Hello, IED. This is going to be our talk on Activity 2.3.1, Material Properties. And our goals for this lesson is to list material properties that are important to design, including mechanical, chemical, electrical, and magnetic properties. Also, perform an experimental protocol to investigate a phenomenon and or gain knowledge. Also, conduct non-destructive tests, hardness, flexure, conductivity, on different material types to investigate material properties. So this is going to kind of be a two-part. The first part, we're going to mainly talk about the how to determine the density of an object, and then after that, we're going to try to determine other properties of an object. So we're going to need a lot of different stuff. And if you're virtual and you're not in class, then you're not going to be able to do the activities, but I'm going to have videos up for you to help you be able to do these activities at home without, missing out on a whole lot of stuff. It's not the same as being here, but you know what? The times being what they are right now, we'll just have to deal with what we got and move on with life. So, we need to talk a little bit about like the role of materials in an engineering sense, because when you're designing a part, when you're making something, whatever it may be, it's going to have to be made out of something. And that sounds like a very redundant statement, but you actually have to take a lot of thought into what you're going to make this material, what you're going to make this item out of, what materials you're going to need, because those materials are important. They have a price, they have properties that go along with them, and you may end up making the wrong choice if you don't think far enough ahead on what you would actually want on those properties. If you're wanting something that's going to clip to a wall or clip to a whiteboard or something like that, you're going to need something magnetic. It's going to have some magnetic properties. You can't just make it completely out of plastic and be like, okay, it's going to stick, because it's not going to work. You have to be a little bit careful with that. And this is where the whole field of material science comes in. So there are engineers specifically for materials and what those materials can actually do. And it goes into a little bit more of the research category. So, normally we talk about mechanical engineers or electrical engineers, and they do research, but they don't do research in terms of researching materials or researching the different types or trying to find new things. Mechanical engineers and electrical engineers are big proponents of if it's already been done, then there's no need to do it again. So we're just going to use what we've got and work with those materials. And a material science engineer, they're looking for new materials and they're looking for new ways to build things with those materials, or even new ways to mass produce that material in order to get it out to the public for consumption. So there's various different types of materials. They fall into different categories. There's metals, there's ceramics, there's polymers, there's composites, and there's biomaterials. And if you want to go into detail about what each one of those are, their properties and what they do, on the Project Lead the Way website, you can click on those links and they will give you more information about those individual things. Okay, so um, let's see here. It says, the very first thing that it says is with a partner, if you're virtual, just do it by yourself. Brainstorm a list of materials properties or characteristics that a materials engineer would be interested in knowing. So, if you're thinking about like materials, what would be important to know about that material? So, and it gets a little deep, because I know a lot of times people are like, well, its weight is important. Be like, well, that's fine, but you can go into a lot more detail about what is actually important. So, there's a whole lot of different things. Um, the next thing that they talk about is this is kind of like a chemistry term on whether or not a substance is going to a solid substance is going to be crystalline or amorphous. And a good example is like the drawing that they have here. A crystalline substance is going to be ordered, it's going to be properly aligned, and it's going to have some kind of pattern to it. A amorphous arrangement, let's see if I can flip this over. Oh, hey, look, there's some great examples of that. Ice, salt, quartz, diamond, zinc as a metal, and iron. There are actually some metals that exhibit crystalline properties. Bismuth is another example. It has crystalline properties as well too. Here's an example of an amorphous solid. Although a lot of people will look at that and be like, well, it kind of looks a lot like a liquid. And, the drawing kind of breaks down at this point because, yeah, you could probably actually, Liquids are generally incompressible anyway, so to think of a liquid as like spaced out compared um, doesn't really do it justice. So just try to think about like crystalline as it's got some kind of order to it, and amorphous, the order is a little bit, off. Like, is it a solid? Yes. Are the atoms still put together in a particular spot? Yes. Are they going to make a perfect pattern? Absolutely not. They're not going to make a pattern like that. Some great examples of amorphous solids are going to be like glass, gels, wax, and some plastics as well too. So the order of the actual molecules or atoms or molecules are going to make a difference in what the substance actually does. Even so that you might even have the same atoms, and those atoms are going to, because of their arrangement, exhibit completely different properties. They talk a little bit about diamond and graphite. So the graphite that you use in pencils, like for pencil lead, is made of carbon. And if you were to look at the structure of a diamond, it is also made of carbon. So the difference between the two is how they're actually arranged inside. Graphite normally has carbon in sheets, and diamond normally has it in this kind of pyramid-like structure. It's a tetrahedron structure, which is a little bit different. Try to think of this picture right here, which is unrelated apparently, and try to imagine one more carbon in the middle of this, and they're all just kind of connected to each other like that. That's the structure of a diamond. It's very sturdy, and because of that, you may have heard of like diamond tipped blades and stuff like that. It's a very hard substance, and it'll cut and much, much more before it degrades. So, and unfortunately, diamond is kind of expensive because it's rare to find as well too. So you have a better durability, but you're also going to be paying for it with a price. That's why you have a diamond dust coated object instead of like a diamond blade because it wouldn't work as well. All right, so a lot of things that they're kind of looking for a material science is to think about these four different things. Um, Try to think about the performance of the object, how it would actually perform in a real life scenario. Try to think about the properties of the substance, like what it actually does. You don't want it to accidentally have a property that you didn't want it to have. You also need to think about the structure, the atomic structure or the molecular structure of the material itself. And you also need to think about like how are you going to get that material. So, you can make the most extravagant thing in the world that has these like wondrous properties. But if it's so rare that you can't really like use it, then that's something that an engineer really has to consider in making their stuff. Okay. You can also think about like, how are you going to process it, like molding, bending, rolling, welding. A lot of metals are usually rolled. You can weld metals. You can't weld plastics or clays. That's not going to really work very well. Anyway, there's a whole lot of different stuff that you can read about in here. And the first property that they want us to talk about, and this is like the basic one, you've probably done this in physical science as well too, or even in earlier science classes, to determine the density of an object. And density is a physical property. It's basically how much stuff is compacted into one unit of matter. So think of these as two, like, I don't know, Minecraft blocks or something like that. If you've got a high density substance, then you're going to have a whole lot of things inside that one block of substance. If you have a low density substance, then you're not going to have as many things inside that cube. And since you don't have as many things inside that cube, it's going to feel lighter. It's going to because it's literally got less stuff inside of it. So you can have like a piece of steel in one hand and a piece of like cork in the other hand, and they're going to feel very different from each other, even though they take up the exact same volume. They would both look like Minecraft blocks. They would just look very different from each other physically. Okay, so they continue to go on, and in this activity, what we're going to do is we're going to take water and we're going to take an object and we're going to dip it into the water to try to find its density. We're going to find out how much volume it displaces. So there is a set of instructions to go with here. If you are not, if you're virtual, then you're not actually going to have to do this in real life. You're just going to have to watch the video that goes along with it. So it says that, this experiment will test the hypothesis that the density of a material can be used to identify the material. Restate this hypothesis as an investigative question. So what are you going to do? So like we are going to investigate the density of an object so that blah, blah, blah. Continue and fill out that. Based on your observations of the material shape samples before testing, predict the order of the density of the material samples from least to greatest. Record the rationale for your ordering. And then identify independent and dependent variables. So remember, independent variables are the ones that don't change, and the dependent variables are the one that change because of the situation. So the independent variable is the ones, this is going to sound a little backwards from what I just said, but the independent variables are the ones that we change in the experiment. So what I like to say is I like to say I change, independent variable. I change the independent variable. Match the I's up together. And what we're going to be doing is we're going to be testing out different materials. So the independent variable is going to be what we're actually changing in this case. Okay. Um, and then create a data table to record the observations, mass, and volume for each of the material samples. So you can write out the different metals that, or different materials. There's some metals and there's some non-metals that go along with there. Okay. Um, and then from there, it says measure the mass and weight of each of the material samples as directed by your teacher. If you're virtual, watch the video. If you're not virtual, we did it in class. Let's see here. Use the water displacement method to measure the volume of each material sample. Okay, so this is how we're going to actually measure this stuff out. We're going to measure it by taking water and displacing it. So I believe that I think from there we're going to be good. We just need to make sure that we write this out in our notebook as well too. Um, there is one other way to calculate the volume, and it's not using the water method. I believe that if you read the instructions, not like how I'm glancing through these, you can actually record the volume by using a mathematical or a geometric formula. The ones that I use in class, all of the materials are going to be either spheres or cubes. So we can use that information to be able to find the volume of it. You can look up the volume of a sphere or the volume of a cube from geometry, and you can see how that actually works out for you. I think from there, though, I think we're pretty much wrapped up in this case. So we're going to compare the two to each other. There's a lot of information to write here. So they're asking for, which method is more precise and which method is more accurate on determining whether or not you're just going to use a geometric formula or whether or not you're going to use water displacement. Okay, and we're using a dial caliper in order to get the dimensions for it. So and that's going to kind of be up to you guys on the way that you want to go with it. Um, if you're virtual, you're only going to be doing the water displacement method. You're not going to worry about the actual calculation part because we're not going to measure it out with calipers over digital. We're just going to do the water displacement and that'll be good. Let's see here. The materials have the following geometry. Two samples. You know what? All of mine are spheres or cubes, so I don't really think in my class you don't have to worry about the square prism or the rectangular prism or the right cylinder for right here, so I wouldn't really worry about those. The two formulas that you're going to have are spheres and cubes. And let's see, I think from there you can answer the reflection questions and you should be good to go. This video is getting kind of long, so I hope you guys have a great day and I'll talk at you guys later.